here. So you have everybody. You can probably start whenever you want to.
Okay, I think then we will start the next session. Welcome back to everyone. We now have the session on VLBI techniques and arrays. Again, just to our speakers, please keep to the time allocated. I will give you a 3-minute warning, and then for the audience, please remember to post questions in the Q&A. And then our first speaker for the session is Francisco Colomer, and the title of the talk is the Global VLBI Alliance. So you can share your screen.
Yes, thank you, Alet. And thank you to the organizers and the SOC to give me the opportunity to talk today in this session on VLBI arrays about a global VLBI alliance. So what is this? What is this initiative? And what will be the impact and how people can participate? So, well, we are in the EVN Symposium, right? So no need to explain what the EVN is, but also possibly no need to explain that there are other VLBI networks around the world. And many of us are or have been users of several of these networks. Now, the concept of a global VLBI alliance comes because, well, for more than 50 years now that VLBI has been developing truly as a collaborative effort. And as a consequence, we see, as I say, several VLBI networks that are established and running. Many of them offering open skies, therefore any astronomer with a good idea can access one or several of these networks. And each of them have a well-recognized brand. We hear of the EVN today, but also the EAVN, the VLBA, the LBA, the GMVA, SHA, the LOFAR, ILT, EHT, the IVS, well, all these acronyms, some more fortunate than others. And the fact that, well, as we say many times, these different networks, I will go very briefly through some of them, but many times these networks cooperate, and even observe together. We have been finding in recent times that it is often that some radio telescopes belong to more than one VLBI network. And this is the case, for example, of the Chinese telescopes that are both members of the EVN, but also of the East Asia VLBI network. The case of Hartebestoke Radio Observatory in South Africa, which is a member of the EVN, but also a member of Southern Hemisphere Long Baseline Array with Australia. The case of Effensberg and until recently Arecibo, we are members of EVN and also the High Sensitivity Array, the SHA. And that is going to also happen with new instruments that are under construction, the case of the Thailand 40 meter or the GMRT in India, which is now getting VLBI capabilities. So the initiative of a global VLBI alliance is to set a permanent forum in which the representatives from all these networks can meet and can discuss issues of interest. I'll go to that in a second. But also when the VLBI users, that's us here today, can discuss and can present the current issues and future needs for the science. And last but not least, very important, could be a point of contact for collaboration with third-party instruments. We will hear about the SKA, but we will hear also satellites or other instruments and how VLBI networks can engage with them. So the reasons, as I say, is to share information. That is why this is a forum, the VLBI Alliance, is to share information in a timeline structured way, strategies, not only to align them, but even to, well, exploit complementarities. And we saw some of these yesterday at the users meeting, where we said, well, what are the best things, but also the problems on different networks. And I would like these problems to be looked at on this possibility of complementarity between the networks. The science visions, we saw yesterday as well, the EVN science vision, very recently developed, technology paths of the networks, logistics, operations, proposal types, deadlines, not often are the same, scheduling issues, and also it can help to keep an inventory and visibility of the different developments. Also for the users, for the non-expert users in particular, but also for other stakeholders, to have a clear and visible contact point for the different VLBI facilities, and in particular, a website where the different networks of VLBI can be sufficiently explained, and also we will be an entry point for new facilities and new groups. We talk here, for example, of the EVN, the Africa VLBI Network, or the recently established Initiative for VLBI in Latin America, EVN. And together, we can do much better in education and outreach of VLBI. As I said also before, the communication with third parties, the coordination with third parties. These are the VLBI networks who have already been talking and set this concept, this forum of Global VLBI Alliance. This is the Very Long Baseline Array in the USA, the European VLBI Network, the East Asian VLBI Network, the Southern Hemisphere Long Baseline Array, and all of these four, well, not by chance, share one important thing, that is observing frequencies. So all these VLBI networks can, on top of coordinate and exploit synergies and everything, they can eventually observe together. And this is a very important point for the Alliance. And then as an observer for the moment, the Global Millimeter VLBI Array, the GMVA. There are tables here to compare. Of course, I'm not going to read them, but this is also in the video if you want to look later. What would be the different issues that need to be discussed in this alliance, which are ways of access to the networks, proposal types, proposal tools that are being developed and often reinventing the wheel, active project periods, therefore, so proprietary periods, observing cycles, some networks observe 24/7, so continuously, some others only a few days or a few weeks per year, scheduling issues, etc. So you have here the best things of each, the best things of the EVN, the best things of the EVN, that possibly are the, as we said yesterday, the high resolution due to the long baselines, sensitivity due to the big dishes. But for example, in these cases, the VLBA would be better for high cadence observations because it observes continuously. So as we say, we can exploit the different better positions of each of the networks. The EVN, for example, observes in real time, being the only one who does. The long baseline, the Southern Hemisphere long baseline array, which is especially important for sources of very south declination. So all of them have specific advantages, and all of them also can exploit the synergies. These tables are in this document, that it is it's part of a jumping jive deliverable. This is a project in the European Commission, and it was observing how to include SKA in global VLBI, and therefore we had to do this inventory that now is there for your convenience. And talking about SKA, what happens? Well, there is a plan, yeah, and it is we have been working in that for some years now, to include the SKA as an element in a VLBI network. Or alternatively, because it's almost the same, is to add long baselines to the SKA, very long baselines to the SKA. Now, this has been facilitated by this project that I mentioned, the Jumping Jive project. And one of the things that it requires is to set a consortium of VLBI networks together with the SKA. And this kind of agreements can be facilitated if the VLBI networks talk among each other beforehand. And this is one of the roles of this alliance, as I say. Other examples that have worked in the past, very importantly, are when you have missions like this one, like the astronaut VSOP, in which it was necessary to coordinate the observations of the satellite with the different VLBI networks. And again, this actually years ago opened the concept of a global VLBI working group that now we want to do as an alliance. Okay, I'm almost finishing. This is another possibility that we are actually exploiting, in this case for the African VLBI network, and is the possibility to work together to develop training activities In this particular case, the African VLBI network has benefited of the DARA developing in Africa with radio astronomy program in the UK, and also of some of these jumping jive projects. And the consequence has been to have one antenna already in Africa, in Ghana, which is capable of doing VLBI. In the future, we could add to this alliance other instruments that are not sharing frequencies. We talked about the GMP already, the EHT, the ILT, even the geodesy network, IVS, all of them are VLBI instruments. And as we said, maybe not for joint observations, but they will be important to align these things. Now, what is the structure that we are proposing is to have a forum of directors, a forum of science and another of technical experts, and some teams to handle the specifics of operations and communications. And this is how the different groups relate to each other. The advantage or the advance of the Global VLBI Alliance is that already it is set up as a working group in the IAU. In Commission before, you can go to that website and you will see that it is a bit incipient at the moment. And one of the reasons is that the IAU is actually re-evaluating all the working groups now. It will happen in August next month. And as soon as it is possibly confirmed, the Global VLBI Alliance will continue in this forum for another 4 years. The structure, as we said there, the Science Forum, which is especially important for the people today, it is to evaluate and foster the unique and complementary contributions of VLBI to astrophysical research. Therefore, it promotes cross-fertilization, it helps communicating, training opportunities, get together in events. Members of this forum are not necessarily linked to any VLBI networks. This is actually open to the whole of astronomy, and in particular within the working group to the whole of IAU. The technical forum discusses opportunities and coordinates the development of instrumentation, issues like RFI, and it's a natural extension of what we call today the International VLBI Technology Workshop that gives a helicopter view of what is happening in technology. And the other three groups that are in this structure are the operations and logistics teams that it will help coordinate joint observations, for which possibly there will be other tools needed, like MOUs among the VLBI networks, and in particular with third-party instruments. And the communications, not to forget, communication and outreach team to give visibility to VLBI and our networks. As a whole, coordination is this directors forum. And the timelines that we have for this is, well, the working group in IAU is already set up. As I said, to be reconfirmed next month. The teams that are for operations and communications can be established as soon as possible. The astronomers, everybody is invited to join the science forum. And the same happens with the technology forum, even if it will possibly logically start with representatives of the different VLBI networks. And to know more, please stay tuned both to the IAU website and to a website that we are under construction, this entry point, that will be ready possibly just after the summer. So that's all, and I'm open for any clarification or question. Thank you.
Thank you so much, Paragi. That was a very interesting talk. It's now open for questions. Are there any hands? I don't think I see any. We can go to the Q&A. So there's a question from Andreas. Is there any chance that this could help to get weather-dependent dynamical scheduling for globals?
Well, that is for the schedulers team, right, to do. Dynamic schedule is a standard in VLBA. For other networks that have very specific programs set up possibly weeks in advance, it is not a standard, and actually it has been affected by the fact that that you may be bad luck at the time that your observation is scheduled and it is affected by weather. If that would happen, typically you are rescheduled again. Okay, so that it's not like you lose it, but yeah, I think the more flexible the networks become and the more tools we have to do that, even including triggering, etc., the better, and we're working on that.
Thank you. We have another question here from Jack Ratcliffe. Are there any plans for large time allocation legacy type proposal calls that use global VLBI alliance partners, similar to the call by the VLBI, VLA for X proposals?
Yes, that's a very nice question. I think the alliance will facilitate that kind of collaborations. I mean, large proposals are already possible, I think, in every network. But on the other hand, let's make very clear, the alliance is a forum. The alliance does not command the networks. The alliance in its role, it does not have to tell the networks what they have to do. It's only, well, not only, it's very important, to find ways by which the users can be better getting the service that they need for their research. So I think that it will facilitate this, sometimes because the projects need different networks around the clock to pass the observations one to another. And in that sense, I'm sure that these discussions will come up in the operations teams.
Okay, and yeah, there's time for more questions. So there's one from John McKean. So a larger array will place additional pressure on correlator operations, particularly for wide field and FRB type searches. What plans are there for upgrading correlating capabilities or joint correlation?
Well, I'm very happy that John asks this, of course. Yes, I think the possibility to observe together is there, not being the only or not even the main reason for a global alliance. Okay, the global alliance will foster joint observations of networks, but that is not the main role, in my opinion. It's more the forum of discussion, etc. But yes, when this happens, when you have bigger networks, you also pose, you need more resources for the correlators. And this is part of the ingredients that we have to put in the technology for roadmaps. In the EVN technology roadmap, we already do a number of global observations, and also, of course, for the discussion in the technical forums to keep the correlators. Also note that there is the possibility to share correlators. I mean, the fact that you have a global alliance also means that you can send the data from the networks to different correlators in that alliance. Okay, so it will be a challenge, but also new opportunities will open.
Yes. There is an attendee that wants to ask a question if there is time.
Yes, sure, we can.
Can we unmute Chris?
Can you hear me?
Yeah.
Yes.
Just a comment. I think a lot of I agree with everything you said, and you touched on this, but I think this is probably one of the more important things. I think raising the visibility of VLBI, but also the whole political pressure that it will overcoming political pressure, I think it's really important. I mean, I'd say in 10 years' time, many of the ad hoc arrays, such as the East Asian VLBI network, the LBA and the EVN, may well be struggling for existence with pressure from larger telescopes consuming resources. And I think this sort of proposal and give us more ability as a group, particularly as we all come together and sort of with a common ground, sort of say, this is what's needed for the science. So I think while sort of the individual benefits may be good, I think the big picture side is actually really more important, and really is probably the way that we as a group will survive sort of over the changing landscape in the next sort of 5 to 10 years.
That's a fantastic remark, Chris. I see myself VLBI evolving from a network thing to a more fluid situation in which the telescopes and the users can select the telescopes based on their own needs and not so much linked to, in the future to brand network names. But this is to be seen. I agree very much that we working together, we make everybody stronger. And yes, the collaboration is, and the diplomacy that we may use in this collaboration is extremely important in the long term. Thank you, Chris.
Thank you again, Paco. We can now go to our next speaker.
Thank you.
So our next speaker is Maria Gomez. If you can please share your screen, Maria.
Yes.
And the title of the talk is Towards the Determination of Geodetic Positions for the EVN non-geodetic antennas.
Yes. Okay.
Yes.
Hi. Yes,
We
do
can
you hear
see
me
you.
okay?
Yes, we can hear you and we can see you. So you can start if you're ready.
Okay. My talk is in the context of my work. My work is in the context of the Jumping Jive project. And the title is, okay, toward the determination of geodetic positions for the EVN non-geodetic antennas. This work was done while I was working at the Laboratoire d'Astrophysics de Bordeaux. I'm currently working at in Argentina at the University of La Plata. The outline of the talk would be, okay, I'm going to present you the Jumping Jive project. I will make a description of work package 6, in which I involved. The geodetic path and its validation, geodetic experiments in K-band. I will show you some results of EC065, which is one of the experiments in K-band, conclusions and perspectives. Okay, the Jumping Jive project involves 12 partners, as you can see them on the right. Especially, I would like to mention the Jive Institute and the CNRS, because both are involved in work package 6, which is the package we're working in. It is organized in 3 main branches and 10 work packages, as I said. On the left, you have more or less a description of the 3 main branches and a short description of each of the 10 packages. Especially, I'm going to show you something about this, which the purpose is enabling geodetic use of the Jive data correlator. Okay, what do we want to do in the work package 6? Okay, the idea is to implement full geodetic capabilities for the Jive SFC correlator. So in this case, the idea is to proper hand of geodetic sessions schedules with subnetting. In our case, I have to mention that we observe more than one source with more than 2 stations at a time, and after a while, maybe one of the stations can move to another target. So that's why we need subnetting. Attach the correlator model to the correlator output. Attach phase calibration information to the correlator. In this case, phase cal is very important because they help us to align the phase across the channels and to obtain the multiband delay, which is the observable of our interest. We also need, to provide the correlator output in an appropriate format for further processing. In this case, is the Markov format, which will be the output of this. The Markov format will be the input for the HOPS program, which is the standard software for fit in geodetic VLBI. And finally, we would like to validate with real data by using an IBS session. All of these constitute our geodetic capabilities. In the end, we conducted 2 sessions in K-band, EC065 and EC076 in 2019 and 2020 respectively. Okay, how do we validate the path? Okay, we took an IBS session, R1, H72, R1 because it was devoted to the determination of Earth orientation parameters. It took place in December 2018, and it was originally correlated in Bonn. The people in the Bonn Correlation Center, they provided us with the raw data, the correlated data, the fringe fitted data, and the biggest DB files. DB stands for database, which is the current VLBI current format for VLBI geodetic data. and this is delivered for the community for further geodetic analysis. So they provided with everything, and the people at Jive reproduce with their correlator everything, the Markov files, we fringe fitted the data, and we produce the Vigos TV files, in this case in Bordeaux. And we compare the outputs at the level of the multiband delays, single band delays, the SNR, and the whole Vigos DB file structure. So then we obtain the more standard plot. It is a hops output for one of the baselines, and you can see that thanks to the phase calibration information, it was possible and easy to align the phase across the channels, as I mentioned. And then, okay, after making a few experiments and after comparing everything, we can say that the path was successfully validated. And here we have a picture, which is basically the comparison between the correlators. They are the total multiband delay differences in picoseconds against the SNR, following this formula provided by Roches. This is the SNR, and this is the RMS of the bandwidth, which is 720 megahertz in this case, and 90% of the observations are below the cubes of 1 sigma, and the RMS is 5.5 picoseconds. So I think we achieved what we proposed when we said to create the geodetic path. So once we have done this, 2 experiments were planned. They were in K band, 22 megahertz, gigahertz, sorry. And this is because we included the KVN stations, and they observed at that frequency. EC065 was carried out on June 2018, and EC076 in 2020 in October. I think it was planned for June, and then it was delayed for October. Here is the list of all the stations that were included in each experiment. As you may see, we planned to include the Merlin stations, but finally they participated, but were not included in E065, and we will try to include them in E076 in processing. We also included the KVN stations, the 3 ones, but in E065 only KVN Janssen participated. And in the last experiment, we also asked the people to hover to participate, with the idea to improve the geometry of the network, because in the southern hemisphere we only had travel. So in both experiments, we included ICRF resources. The duration of the experiment was 24 hours, and they were scheduled with the NASA schedule by using the sky coverage strategy at each site. And of course, as I mentioned before, the scope was to determine geodetic coordinates for the EVN. Okay, I'm going to show you results of E065 because EC076 is still under processing. It was correlated, but we are in the post-processing stage. So the analysis was done with another standard geodetic software called VIVS. It was developed by the Technische University of Bonn in Vienna. Sorry. Just to remind, the delay, has several components. Here we have the geometry, the instrumental effects, the atmosphere, so the propagation media, and clocks, and many other effects. So we need to measure or model them. So we use the models that we have on the right. It is not a full list of models and etc., but we use many of we use this. You have the C04 Earth orientation parameters. The reference frame was for terrestrial site was ITRF 2014. The celestial one was ICRF3 and many others. And we estimated station coordinates with respect to ITRF 2014, as Earth orientation parameters, tropospheric parameters, and clock parameters. Finally, of course, the goal was to focus our analysis on the determination of the coordinates for Jodrell, Jarvinia, KBN, Yonsei, and Torum. Here is a picture of the receivers per stations. In every plot, we have an observation done by the mentioned station. So, for example, here for this plot, we have the same Badari and FSV, as well as Onsala Badari is the same. And what we can say from this is that we don't appreciate any difference between the non-geodetic telescopes and the others with respect to residuals, so they are at the same level. These are the 4 non-geodetic ones. They are all at the level of the centimeter. As expected, we have that the lowest residuals come from the biggest antennas, like FSV, in this case Sardinia, Jeves. In this case, the KBN Yonsei antenna has not the best residuals, and probably because we couldn't use all the channel, we use only 5. The same happens for Noto. We still have to continue the analysis maybe with Jodrell 2. And finally, the station coordinates got the position, the error in the position that we have here, more or less around 1 centimeter, sometimes better. So we have an estimation for this for the coordinates of these antennas. So what we can say until now, we have a new geodetic path that was established and validated at the EVN jive correlator by using an IBS experiment. We have also shown that standard and non-standard geodetic sessions can be processed from beginning to end with the jive correlated data. So from fringe fitting to geodetic analysis. The estimated coordinates of the non-geodetic telescope are at the level of 1 centimeter. And we plan to include the results of E066 in order to get a combined solution for the coordinates of the 4 geodetic telescope and some others that were included in E066 or the others. And okay, finally, the geodetic path is now available for all EVN users. We would like to thank the people at the Bonn Correlation Center for providing the IBS data for testing and some support, to the team in Hobart for the participation in E076. And okay, the research was funded by the An Horizon 2020 project, the Jumping Jive, and RadioNet. Thanks.
Thank you so much, Maria, for a very interesting talk. Any questions for Maria?
Yes,
Okay.
there are 2.
Okay. From Taiyun Young, he says, thanks for the nice work. Just comment about the experiment EC065 for KBN Yonsei. Unfortunately, it was raining during the observation. That's why you got the relatively high residuals. So now you know. Thanks, Taiyun. And then from Sandor, did some of the EVN stations in EC065 have accurate positions earlier? If so, what can be said about their motion?
Okay, yeah, there was a previous estimation in 2001. It was work done by Patrick Charlot, the precision, the position, the accurately was about 5 centimeters. And we have made an estimation of the motion, and it's around 35 centimeters in these 20 years, more or less. So we can say that it's in agreement with the plate tectonics models we have until today. But we would like to make a better estimation on the velocities once we have E076, because we will have 3 epochs.
Thank you, Maria. I actually also have a question and maybe also a comment for you. Do you plan to do more of these geodetic sessions at K-band? And specifically, I'm asking this question, the current 22 gigahertz celestial reference frame is in desperate need of more north-south baselines. So it would be absolutely wonderful to do some celestial reference frame geodetic type or astrometric type observations, including some EVN antennas.
Okay, the project is finishing now. So from my side, I don't know, but I think that probably it will be of interest to make this kind of geodetic experiments at that band.
Thank you. Thank you so much, Maria.
Thanks.
So we have at least we have a comment from Paco in the chat. So he says, this is not a question, but a confirmation that Jive is now capable of processing geodetic VLBI experiments. This is very important for those EVN stations and others who are not equipped with S6 or VGOS receivers. So that's...
Thank you, Paco. That is wonderful news. Okay, I think then, thanks again, Maria. We can then move on to our next speaker. So if you can please just turn off your screen sharing. And then our next speaker for today is Roberto Ricci. And Roberto, you can please share your screen. And the title of the talk is VLBI Experiments with the Dissemination of a Common Clock via Coherent Optical Fiber Link.
Okay, good afternoon, everybody, or whatever time you are in. And my name is Roberto Ricci, and I'm going to present. I'm going to present this talk on geodetic VLBI, optical fibers, and atomic clocks. This is an international collaboration. Institute in Italy. There are the Institute of National Institute of Metrology, and then the Institute of Radioastronomy of the National Institute for Astrophysics, and the Italian Space Agency. We also collaborated with a list of institutes from Europe, antennas that are part of the EVN or not part of it. The overview of my talk, a brief introduction why the fiber optics clock VLBI connection is important, the Italian quantum backbone reaching Matera, and then a few experiments that we performed on common clocks with optical fibers. So why the dissemination is important of frequency from atomic clocks is important. We have here that millimeter VLBI above 80 gigahertz can be benefit from atomic clocks that are better than H measures, and also the possibility of study compact radio sources and interstellar molecular clouds at a better resolution. Also in a geodetic VLBI, accuracy at a level of 1 millimeter can be achieved with better clocks, and also the study of pulsar to absolute accurate time. Also, there is a relativistic geodesy that is a possibility using optical high-performance optical atomic clocks, and in this case, the technique is called chronometric leveling, and it is used to study the absolute height and using the relativistic gravitational shift. And the third important point is the clock metrology. So it is possible to build, and is being built across Europe, a network of optical fibers links connecting the national meteorological institutes in a way that optical clocks in these institutes can be compared effectively. In the Italian case, the Italian quantum backbone is an optical fiber link that is 1,800 kilometers long, and it serves radio astronomy, ultra cold atom physics, the space Galileo network, and the station in the Fiumicino Plain, and also the financial district in Milan. How does it work? The link, the optical quantum backbone link, effectively uses a phase noise cancellation scheme, and also optical frequency comb to convert and down convert a laser signal from a radio frequency signal. So you can stream initially between Torino, INRIM Institute H masers, and Medicina station H masers, and then later to longer distances. A frequency reference that has an instability over 1,000 seconds of less than a part in 10 to the minus 19. The IQB reached Matera in November 2018. This link now has a 1,800 kilometer backbone. It is divided in 4 spans. The first one reached Medicina. The second span reached Florence, the Linear Institute for Institute for Nonlinear Spectroscopy, and then the third leg reached the Institute for Optics in Pozzuoli, and the fourth leg, the Space Geodesy Center in Matera. This is a brief description of schematics of the way the frequency link in Matera works. And on the bottom left part, there is a picture of the time and frequency lab in Matera with the optical frequency comb in the center. This is the first light of the frequency link, the IQB frequency link, in particular the power spectral density of the frequency signal. And one can see that there are a few lines here in this comparison between H masers in INRIM and Matera, and INRIM and Medicina, that are related to interference that can be worked through. The first common clock geodetic experiment, the VLBI geodetic experiment, was performed in May of 2019. It was a 24-hour standard geodetic experiment in a SX band, and it involved the Medicina, Matera, Yebes, and Onsala antennas. Matera and Medicina were sharing an H maser reference frequency signal from the National Institute INRIM in Turin. The analysis was performed using the NuSolve geodetic software package. We have obtained 58 picoseconds in the WRMS of the group delay post-fit residuals. The clock difference the clock drift between Matera, relative clock drift between Matera and Medicina was 0 within 10 to the minus 14 seconds per second, confirming that Matera and Medicina were working on the same frequency reference that was remote, that was the goal. This was published in the paper on Optica, Clivati et al. 2020. Further geodetic experiments, VLBI geodetic experiments, were performed in November 2020 and in January 2021. And the first one, Rapid 1974, we had a good performance in terms of the post-fit group delay residuals, 16.4 picoseconds, and also the clock drift uncertainty was of the level of 10 to the minus 15 seconds per second. The second experiment had problem with unlocks, in particular 7 unlocks in Matera and 3 in Medicina. So the link wasn't stable to the point of having a possibility of monitoring and determining the impact of common clock architecture on the post-fit group delay statistics. So this aspect is still to be determined, even if the post-fit residual WRMS is on the terms of 30 picoseconds. Second part of the talk, I'm going to talk about briefly on VLBI clock timing. So we perform a series of experiments possibly in winter season on a bright geodetic standard calibrator using mid-high telescope elevation in scans of 15-minute length. And the goal is to get the RMS phase noise statistics following the scheme by Kralik et al. 2017. So we performed a list of experiments between November 2020 and February 2021. In particular, the second to last experiment, WT012, was performed with the Matera Medicina receiving the remote clock reference from Torino. All experiments were performed in X-band, and the last 2 experiments have all the 4 Italian antennas for the first time working as VLBI antennas together. And we perform observation using a receiver operated by the Italian Space Agency at Sardinia Radio Telescope. They're working in X-band for this purpose. Results showing the time delay RMS computed from the THEZA RMS statistics using the formula on the top right shows that for the experiments there is a wide scatter and also a large scatter between baselines, and the most prominent effect is due to the troposphere, as was expected. And so now I'm modeling the theoretical, creating a theoretical model so that I can study the uncertainty, also determining the fractional frequency difference from the interferometric phase scatter, and also the tropospheric, ionospheric, the source structure, the instrumental, the geometry, and the antenna delay terms. One can always see the effect of the signal to noise ratio in the scatter on the phase, interferometric phase through this plot. in particular, the baseline with the Matera were the most affected by a large scatter, and also they have a low SNR with respect to the other ones. So my conclusions, the Italian quantum backbone, formerly known as LIFT, is an infrastructure that is able to deliver frequency reference signal from the Italian Meteorological Institute, INRIM, to a remote location for radio astronomy, but not only, with an unprecedented stability of the order to 10 to the minus 15 in terms of the Allen standard deviation. And we performed a set of geodetic VLBI experiments starting in 2015 that were published in earlier publications with remote frequency standard provided by INRIM. And we found that they are on par with utilizing experiments, local clocks experiments. And the IQB reached Matera in November 2018, and now it spans 1,800 kilometers fiber optic link. We performed the first experiment with common clocks, so Medicina and Matera were served in terms of the reference frequency reference from remote through this link, optical fiber link from Torino, and the result was published in last year in 2020. And also we performed this frequency RMS interferometric phase noise experiments to study the statistics on the scatter. And we performed the first common clock radio VLBI experiments with the 4 Italian antennas in February 2021. And we are in the process of determining the fractional frequency difference on those baselines. Briefly, future developments. On the geodetic side, studying VLBI versus GPS time stability in CON17, in particular for the co-located station with respect to the Bethel antenna, Bethel station. And also we have an ongoing collaboration with the Korean colleagues to have optical clock comparison between Italy and Korea using K-band geodetic VLBI. And also a collaboration with the Italian Space Agency to study VLBI through the delta door, the differential one-way ranging technique. That's it for my talk. Thank you for your attention.
Thank you so much, Roberto, for the very interesting talk. We can now go to questions.
Yeah, so we have a number of questions. The first one is from Richard Dobson, and he asks, so when will you retire the hydrogen lasers?
So the point is the backbone, this optical fiber link is a service, is going to continue operating, but there is no plan now to retire the optical measure at the Institute, in particular the radio station in Medicina and the Space Geodesy Center in Matera. The point is the H measure will stay as a backup at least, but the stability of the optical fiber link needs to be improved yet, so that the service can become the primary frequency standard.
Okay, yeah, connected to this, there is a question from Francisco Colomer. What is the cost of an optical clock compared to a hydrogen laser?
So the performance of the optical clock in terms of stability is a factor, let's say, a 2 order of magnitudes better. So it would be an improvement, a large improvement, if one could use it in a network So optical fiber links connecting telescope operating above 100 gigahertz. That could be helpful both in the phase noise jitter determination, but also canceling out the effect of the clock relative clock instability in the correlation and the VLBI determination of phase stability structure, substructure. So I would say for millimeter VLBI would be optimal. And the idea of having one clock per station is impossible because optical clocks are not commercial at all. They are still themselves experiments. And so connecting optical clocks via fiber links would be the ideal things.
Elite, is there time for more questions? Because there's two more.
Yes.
Okay. So because there are two more questions regarding the fiber network operations with the clock dissemination. The first one is, how challenging was it to engage the fiber network operations in the success of these tests? And would this be available for regular use?
Okay, let's say at this moment, the coordination is still difficult because, as I said, there are 4 legs with 4 regeneration for the optical fiber links, for the optical fiber link, the IQB, and also coordinating the observatories was not easy because this was done outside normal operations, let's say in the test. In particular, 24 hours of a continuous operation for the geodetic experiment was still a bit of a challenge. It's doable, but still a bit of a challenge in terms of logistics and also stability of the operation. It's not to be offered anytime soon for regular observations. We have to test yet a lot before this could be offered.
Then we have an attached question from Sander Frey. Technically, is it possible to extend this clock dissemination method beyond Italy? And is there a sufficient optical fiber network for this?
So nowadays, INRIM has a connection between Italy and France. They can reach the National Institute in Paris. The Germany is also connected, but the point is avoided unlocks. So for a continuous operation, one needs to think about it. But of course, the optical fiber network across Europe is increasing and speeding up. And so it might reach also easily location where EVN antennas are.
That's excellent news. So I don't see any more questions nor raised hands.
Okay, then we thank you again, Roberto. And I believe we now have a short 10-minute break. And then we'll start again at 4:10.
Great job, ladies. Very nice chairing.
Thank you. Sorry, Kasi, I was probably too excited at the start, and I
no, totally fine.
Questions, but...
So, Alan, after the break, is it me or Richard Dobson?
It's Richard first, and then you.
Okay. I thought you. I thought we have this break because Richard is not coming. All right. My talk will be short anyway.
What? Why is Richard not coming?
No, Richard's coming. Everything's fine, and it's just a good program.
Yeah, I was just surprised about the break.
Yeah.
I guess that everyone really has gone for a cup of tea, except Zsolt, maybe.
I'm also around, but
Okay, could you, can I just try sharing this?
yeah,
Sharing
1 second. Yeah, now you should be able.
That one. That. So I'm trying to dual screen this presentation.
Okay, we got the right one.
And I've got my notes, so we're good.
And it changes, yeah.
So. Okay, if you want to put back it's a break, that's fine, or I know I can come back to this.
Yeah, okay. Yeah, it seems to work, so it's not a problem.
The real pleasure here is trying to read what's on Zsolt's bookshelf. He doesn't know we're doing it.
I think he's not listening now.
No, we can talk about him and he doesn't know.
No? Only maybe the other 80 people, but not him.
Denise has got an intriguing sign that says integrity. That's been attracting my attention for weeks now.
You started last week with the symposium, with the seminar, no? And then this week looking at that.
Yes.
How is there? It's getting late, no? Now.
Yes, Alice. Well, 10.
Okay.
10.
Yeah, at least we don't force you too much. Too late in the night. But...
No. Normally I'd give a talk and go out for a beer, but it's just not an option.
Late one.
Well, I would like to welcome you back from after the break. We will start with a talk by Richard Dobson, Foundations for the Ultra-Precise VLBI Astrometry in the SKA Era. Please go ahead. I will give you a warning 3 minutes before the end. Richard?
Richard, you are muted. Richard?
Yeah, I'm just trying to find where that unmute button had moved to.
Cool.
Yes, first of all, thanks, of course, to the committee for the invitation to talk about this work that Maria and myself have been doing on astrometry, particularly focusing on the next generation of instruments, which we think has produced some very interesting answers. What I'm going to try and cover in this talk at quite a pace is how to achieve what we're calling ultra-precise VLBI astrometry. So it's an order of magnitude improvement over an order of magnitude frequency range, going from 3 meters to 3 millimeters and beyond. This is the outline. So the new horizons that have come with the SKA and the NGVLA, which are on track to be in the next few years, where few is an undefined number. we are on the cusp of a new domain, a new era with new opportunities. We'll have 2 orders of magnitude improvement in the thermal sensitivity, but this does not improve the astrometry, and that's a very important point to realize. The systematics are the limitation, and so we've been focusing on the methods that can provide ultra-precise astrometry. There's 2 key opportunities for the EVM, we believe. That's in the development of these new methods in both multi-view and source frequency phase referencing. This is a sketch from our review where we've tried to capture everything, starting from a single dish of a moderate size connecting to a large dish, a tide array, instruments, space VLBI. PowerPoint is using my last practice of this talk to do the transition, so I'm losing control. So apologies for that. The technology that needs to be provided is on these larger dishes, on the tide array beams from the arrays and the multi beams from the larger dishes to match the field of view of the smaller antennas. Combined with that, with those multiple beams, you can match the effective field of view of the smaller antennas and the bigger antennas so that you can do multi-view VLBI with multiple targets. And also you can cope with multiple frequencies for source frequency phase referencing. The phase referencing is a pretty well-established method. It's been used right since the beginning of VLBI. And it's traditionally done by switching between the two. You observe the calibrator and then the target, and at the same frequency, you switch between them. That has astrometry information is then embedded inside the differential, the phase differential observation that you form, and that is combined with the calibration terms, the systematic errors you need to remove, and ultimately limited by the sensitivity of the thermal noise. So the current instruments, this is really irritating me. The current instruments are set giving systematic limits of 100 microarc seconds, which fortuitously, or maybe by experimental design, are more or less where our thermal limits are as well. And with the next generation of instruments, we're going to have 10 microarc seconds thermal sensitivity because of this order of magnitude improvement. And so now we need to develop new methods that will bring the systematics down to a common level. And in addition to that, we've introduced this re-expression of the well-known phrase, set of phase terms into what I've been calling the Rioja relationship, where we've introduced a factor R, which allows us to represent with one set of equations the references goes beyond these established methods. It can be the target source or another target source or multiple other sources. It can be at the same frequency as the target or at different frequencies. All of these are captured by this one expression, and then you've just got a calibration level that you need to, the calibration phase, the error in your calibration, and an error from the thermal measurements. And these are the two things you need to control to get good astrometry. So turning to the historic results, here we plot the thermal noise from a dynamic range of 100 to 1 with a gray dotted line. And that's the typical level of sensitivity you'll achieve with a normally scheduled experiment. Against that, we've plotted systematic calibration errors, which are the multicolored lines, black being the conventional phase referencing with a 1 degree separation, and green and blue are the advanced calibration methods, such as geoblocks or UVPAT to reduce the tropospheric errors from 3 centimeters to 1 centimeter, and the ionospheric corrections, which could be those dating back to the SX receivers or ice blocks that have been developed recently, or Walter Briskin's method for his pulsars. That's to be compared with in-beam phase referencing, where you simply found a calibrator that is closer, and you've used that nearby position to do the beam dilution. And then finally, we plot the errors for the multi-view method that we've been developing, and you can see that's well below any of these. Overplotted are various experimental examples, and they match the theoretical lines very well. So we're quite pleased with that. Finally, I had SFPR predictions and actual experimental values. So that's where we are today, and we're wondering where we could go with the next generation of telescopes. So we've extended these theoretical curves to ask what do we need to do to have to be able to make astrometry with a dynamic range of 1,000 to 1 that we expect from the SKA. Now you can see the in-beam phase referencing with 10 arc minutes is well above, the systematic error is well above the thermal noise, but the multi-view is a very good match to it. And I should mention that this multi-view curve that I've plotted there is based on measured residuals as measured by the MWA and the SMA for the ionospheric and tropospheric residuals residually, respectively. In-beam calibration is just not going to be able to produce the astrometry we need to. So we've been focusing on what the key technological requirements are. Oh, this is so irritating. To enable ultra-precise astrometric measurements, and asking what demonstrations we need to show what is needed for SKA, SKA low, SKA mid, NGVLA, and even potentially the next generation EHT. So the multi-view fact sheet I give here is basis of multi-view uses 3 calibrators surrounding the target as in the diagram above, and you make a 2D interpolation to the target in the visibility domain to provide the corrections at the position of the target. 3 calibrators allows for a planar fit, but if you have more calibrators, you can fit for higher order terms. This removes all the systematic residuals and antenna position residuals, which is relevant for space VLBI. And so it provides everything that astrometry and phase referencing has done previously. Here's the demo from 2017, Maria's first author, and we are plotting the systematic results from conventional phase referencing with 6, 4, and 2 degrees separation compared to the multi-view result, which is thermally limited. And also plotted is the phase referencing of the in-beam source we also had in this case. The domain of the application is really for multi-view, it's all regimes. High frequency and low frequency are equally good. I do apologize for these timing problems. The optimum performance comes with simultaneous observations, and therefore the key technology to be demonstrated is tide array beams for arrays and multi-beam beams or PAFs for the larger dishes. And there's been a whole string of empirical demonstrations, well, not a string, but 2 are published, 2 more are coming, and there's been feasibility studies. So where are these numbers coming from? And I'll deal with this quite quickly. We've been looking very hard at the MWA results, looking at the phase screens over the antenna. And then we've been reusing this information, which was for an entirely different purpose, to predict, after characterizing the ionosphere, we predict what the multi-view residuals should be. And we're finding that they're going to be typically 1 millitech over 1 degree. That's our predictions for the SKA performance. So this is the kind of thing we'd be seeing for the frequencies on the left. We predict the number of in-beam sources based on TREX from Anna Baldini, and therefore we can calculate what the multi-view error would be. And for 1.6 gigahertz, for example, it will be 6 microarc seconds, and that's about the highest frequency you can do in-beam multi-view. For higher frequencies, you will be looking to do switch multi-view, so they're no longer simultaneous. Estimates get a bit difficult, but we're going to pick a number out of the air and say 1 microarc second residual error. Now, the phase screens, we used to say 10%, and we've been digging in a bit more recently, and we're now saying or more, 10% or more of the phase screens, so significant curvature. So because of that, we're recommending more beams. We recommend 7 calibrators will be the thing to guarantee you this microarc second position. So turning on to where we might be able to do this, the current site suitable for multi-view VLBI, for ultra-precise pulsar astrometry or any other L-band astrometry. We can see that suitable sites, large targets are Parkes, FAST, Effelsberg, Jodrell, Westerbork with their tide array beams, Sardinia with their multi-beam, GMRT with their tide array beams, and proposed ASCAP with a tide array beam, Meerkat, and compact array. So there's lots of sites with sufficient sensitivity. We've got some corner case demonstrations that we've been looking to do to prove. I mean, we've made this statement, but we haven't proved it yet. So we're looking at this low elevations and low frequencies. And I'm going to talk quickly about low elevations. We're working with Mark Reed on that one to extend the Bessel observations into the inner quadrant. Now, for conventional astrometry, you do not go to low elevations because there's a sec-Z effect in the errors. So your errors are huge at low elevations. But multi-view should correct that. So we've tried it. And certainly the phases are looking very linear. And I've got the phase screen above, and plotted is the residuals. The residuals are very clearly in the elevation. So I think we're really seeing a second order in the sec-Z effect. So we should be able to improve on that. But the main challenge is developing methods for dealing with or making sure you haven't lost any of the ambiguities. I just wanted to say a quick few words about source frequency phase referencing. I'm sure it's been covered in previous meetings by people from the KVN, but that's another calibration method where you use multiple frequencies as your reference and target, and then deal with residuals by slowly switching between 2 sources. It's been terribly successful. Here are some SIO masers going up as high as 129 gigahertz, and they are completely registered. These are showing the emission, the maser emission, and how the various spots relate. So that was a very pleasing result. There's been lots of demonstrations from the KVN. They're building this compact triple band receiver, which is being bought by a number of the European telescopes, and lots of demonstrations and some feasibility studies. The global millimeter multi-frequency VLBI array is growing. There's KVN, plus then there was Yebes. Now there's been connections to the Vera antennas, to Australian antennas. Thailand's been built and will be compatible because it's the same as Yebes. And there's the center of gravity of this SFPR array is moving towards Europe. So I think there's a strong ground for doing lots of work there. There's been a fair amount of work on how to do it and why to do it in those publications. And then I'm reaching my summary. Astrometry rapidly reaches systematic limits. So increasing your sensitivity does not improve your accuracy or your precision, to be more precise. So your ultra-precise astrometry requires new experimental methods, and those are exactly what Maria and myself have been developing over the last few years. Multi-view and SFPR addresses these requirements, and I think we addresses them completely. We're certainly very pleased with the results. A good number of EVN telescopes support or will support multi-frequency millimeter VLBI, and there's many demonstrations of SFPR being performed. There's a lot of open questions still in the method, so I hope that people will investigate those. Demonstrations of multi-view VLBI for the SKA planning are also required, and many aspects are very suitable for EVN partners, particularly given your close linking to SKA VLBI. And one thing we would particularly like to see demonstrations of is doing simultaneous multi-view with paths and tabs, because I think that's a really important demonstration, and it's a remaining open risk in SKA VLBI. It should work. There's no reason for it not to work, but we haven't really demonstrated that. So that's something that I hope places like Effelsberg, ideally working with us, we'd really like to be involved, but there's a lot of EVN partners who have got exactly what is needed to just prove this is going to work as well as we're predicting. And that essentially is my final point, which is for some reason is not appearing. Okay, yeah, there it is. So ultra precise astrometry, there's a lot of science that can be done with 1 microarc-second resolution, astrometrical precision, not resolution. There's a lot of details in that review, and I would recommend reading it and discussing any questions with us. But that's all I've got to say now.
Thank you, Richard, for the interesting talk. I think we have time for maybe one question.
Well, the first question was Andrei Lobanov that raised his hand. Can we unmute him?
Yes.
Here. Hey, Richard, thanks for the excellent talk. I just had a long question. That was going to be a short question. When you're talking about multi-view precision and going to micro seconds at low frequencies with SKA, how about these scattering? So a lot of sources will be scattered well beyond that accuracy.
These are the unknowns in our expressions. So we were actually more worried about jitter than scattering.
Okay.
These are unknowns. So while we're gaily saying that we should be able to reach 1 microarc-second, every time you remove a systematic limit, you reach the next one. I don't have, do you have a scattering number to have? No, so we don't actually have numbers for that. But yeah, it's called, we thought core jitter would hit us before then.
Okay. And then the rest, we should get in touch outside of this panel.
You know where to find us. On the beach.
Thank you again, Richard. If you can please stop your screen sharing, and then we can go to our next speaker, which is Zsolt Paragi.
Richard, I just want to say I will put the questions that have remained into Discord, so you can answer them there.
Okay.
Thank you, Kasi. Thanks. And then Zsolt, you can share your screen, please. And the title of Zsolt's talk is TeraHertz Exploration and Zooming in for Astrophysics. Thank you.
Hello. So do you see my screen now?
Yes, we can hear you. We can see your screen, so you can start.
Fantastic. So this is the last presentation. I promise this will be short. I'm actually giving this presentation for Leonid Kurvitz, who unfortunately cannot be here, but this is his initiative, this THEZA concept. So let's introduce it quickly. So every now and then, ESA announces a call for proposals, for ideas, for missions, scientific space missions. So this is part of their long-term planning process. And then for this call that was released a few years back, there were a number of papers submitted, and 95 competitive mission ideas were actually received. So just to mention one, there was a proposal to continue the Gaia mission, to go much deeper and actually go also to the longer wavelengths, to near-infrared wavelengths, so you can also detect stars that are obscured in the optical regime. So this was the call a few years back, and we submitted this THEZA white paper to this call, which is in principle a concept of space interferometer working at near to terahertz frequencies. So this was facilitate a major leap forward in spatial resolution and fidelity for imaging black holes. That is the idea. So this white paper was published on Archive and also in Experimental Astronomy. Now, as you all know, space VLBI has been realized already. So there were 3 missions, successful missions. The very first one at the end of the 80s was a demonstration experiment for a few quasars using the THEZA satellite. But after that, there were 2 missions, the Japanese led VSOP mission, and then the Russian-led radio astron mission. And they were both very successful, demonstrating how science can be done with baselines exceeding the Earth's diameter a number of times. And radio astron actually went up to 22 gigahertz, producing lovely fringes in that regime. So there was an idea to extend to have another VSOP mission to go to higher frequencies, but unfortunately that was not realized. On the other hand, we have a heritage of sub-millimeter space astronomy. A number of satellites have been in space, like the SWAS mission from NASA, the Swedish Odin satellite working in sub-millimeter wavelengths, Herschel, Planck, and there was a very strong competitor, Spica, from Astro, but unfortunately it was decided that this M-class mission will not be realized. But the millimetron concept is still alive, and this would be a 10-meter antenna flying at the L2 Lagrangian point, and that would do single dish astronomy at the frequencies, and also some space VLBI as well. Now, what is the science? Yes, we know since these lovely EHT results that black holes do exist, and that particular black hole shadow, that's the result of light bending in very strong gravitational field proposed some 20 years ago by Heino Falke. So this really exists. And this opens up an exciting new field for studies. Now, with the current EHT, you can study only 2 black holes, M87 and the galactic center, and we are waiting for those very exciting results. But of course, we would like to improve the fidelity and resolution of these results, so we can probe the GR more to more detail. So if you have a resolution that can probe the event horizon scales and high fidelity images, then it opens up an entirely new set of tests for the general relativity. Like you can measure the spin of the black hole very accurately, probe the no-hair theorem. You can probe the structure of the space-time, and you can even probe black hole alternatives. And I'm very glad that this dilaton black hole was already introduced earlier at the EVN Symposium, so I don't have to explain. So this is this exists in a modification of general relativity. And whether a black hole, what we see is a Kerr black hole or a dilaton. Well, if you want to make a difference between these, then you really need very high fidelity imaging and resolution of around 10 microarc second, and this is what the figure here demonstrates. And also, you could possibly map magnetic fields around black holes. This is also done by the EHT for M87. And then this way you can probe accretion, ejection events, and especially all those phenomena that lead to jet ejection and collimation. Now, what is the resolution and fidelity we need? So the left figure shows you a study that investigated this, how accurately you can recover the spin of a black hole from certain measurements. And the spin recovery accuracy, well, for the 0.2, that is more or less random values, and more accurate values come above 0.8 or something like that. And if you look at the x-axis, then you see that in order to achieve this, you need resolutions at about 5 microarc seconds or so. So how you can do this? You cannot do this from the Earth, because the EHT is limited to the 22 microarc seconds in resolution. So you either need higher frequency, or you have to use space lines. Or actually, you can do both. And when you do that, just a demonstration for 3 supermassive black holes with different masses as a function of redshift, what would be the size of their horizons. You can see that not just these 2 black holes, M87 and the galactic center, but a number of other black holes would be visible. I believe about 8 other black holes nearby, but also for the most massive black holes, you could resolve them in the entire universe. And beyond that, of course, you could study the inner jets of AGN, and in particular that few hundred to 1,000 Schwarzschild radii, that is very important in jet collimation and acceleration, because the bulk of the jet acceleration happens at these scales. But to study these scales, you need a resolution that is finer than this, and that requires about 10 microarc second resolution. So these simulations show, on the top you see 2 different kind of jet models. It's hard to distinguish by eye. And then in the lower panel, you see an actual VLBI image of M87, and the other 2 are the simulations convolved with the beam of the real observations. And it's clear that with this resolution, you cannot separate these 2 scenarios. Also, we heard about recollimation shocks during the symposium. So with the space VLBI, you would be able to directly resolve these sides of the physical processes to measure the jet power and actually to see how it's related to the spin accretion rate and the magnetic fields. And if you see, for example, features like knots in the jet, whether this is actually a traveling shock wave or a recollimation shock with this very specific edge brightened structure, then you really need to go to space to achieve these kind of resolutions. One of my favorite topics is, of course, binary AGN, because you can imagine that even if you cannot solve the horizon of all black holes, but you could possibly see a number of dual binary AGN that could not be resolved by our ground instruments. So why are they so interesting? Of course, the growth of supermassive black holes goes through phases of intensive accretion and merging. And you know that galaxy mergers play a very important role in the evolution of galaxies and black holes. Now, in this case, you may assume that after some time, pairs of supermassive black holes may form, and then these black holes would come closer and closer to each other. So there are various processes that are important here, and these processes are different on different spatial scales. So first it would be dynamical friction, then stellar scattering, and then gas may play some role at 10 parsec scales and below. And finally, a few hundred to 1,000 Schwarzschild radii gravitational radiation starts to kick in. And that's the regime where we start to see gravitational waves with the LISA. Now, this particular range could be possibly resolved with a space VLBI interferometer. And on the right-hand side, you see different lines for different mass ranges, and depending on the distance, what kind of resolution you would need to separate these black holes. Of course, one of the issues with the binary black holes is that it's only a fraction of the black holes are radio loud. So what are the chances that you have to radio loud the AGN in a system like this? Well, it appears as these black holes harden their orbit, the chances are that at close separations, both of them will form a mini disk, as it's demonstrated in the simulations on the left-hand side. And usually these black holes form efficiently in minor mergers, which means that the black hole masses are very much different. In this case, it is always the smaller black hole that wins, in a sense that most of the accretion will happen there. What happens is that the smaller black hole will be highly super Eddington, while the larger black hole will be sub-Eddington. And these are both regimes where you expect that they can be radio loud. Now, you have to measure the separation, the numbers, statistics of these black holes and various separations in order to find out the efficiency of the various processes of black hole orbit hardening. And then, of course, just quickly, there are a number of other ideas for space interferometer to study, but these are the more complicated cases. We know that transients are very compact initially, and especially galactic black hole binaries. The jet base is near TeraHertz frequencies is expected to be in this kind of angular regime of 40 to 400 microarcseconds. So it could be resolved by a space interferometer. And similarly, the orbit separation is expected to be in this range. But unfortunately, these black holes are only bright when they flare, and that's of course very tricky to observe them in that state when they are very highly variable on a very short time scale, and otherwise they are very faint. Water maser science, that's very exciting for both galactic stellar astronomy and also for AGN. So there are about 100 maser transitions predicted between gigahertz and terahertz frequencies, but only 10 have been detected so far. And for example, around evolved stars, you can see the various transitions, water maser transitions, tracing the different conditions in the envelope appearing at the different separation at different radii. And then in AGN, you can use this water maser to trace both star formation and AGN activity. And this was demonstrated by Willem Baan with radiostron, these can be extremely compact on space baselines as well. Now, you could possibly detect water in protoplanetary disks as well. Water can freeze out on dust grains in disks shielded from radiation, and these ice lines trace planet formation. Now, what kind of water lines you detect? You can study the various phases of the gas, but for this you also have to go to space because of the high frequencies. Unfortunately, these are very extended, so you don't actually need the resolutions of a space interferometer. You could possibly detect exoplanets, so these are becoming more and more ambitious goals, of course, but just an idea. I will not go into the details here. And also, if we are talking about planets and life, we could possibly also look for technosignatures, SETI. Well, this is an interesting possibility as well. We know since the Kepler mission that there are many planets out there, and about 20% are in habitable zones. So why look for technosignatures in this particular frequency regime? Well, wide bandwidths and ideal for long distance communication, we can probably catch signals from other civilizations. Now, one possible implementation for THEZA was already considered as an event horizon imager. So this would be 2-3 satellites, 4 meter class antennas flying on low Earth orbit. And actually, so the orbital radius would be very similar. And after a few months time, you would slowly fill in the UV coverage with just a few number of satellites. And the idea is that you would average these visibilities in the UV plane, and you could image an average image of the black hole itself. So this should be in the frequency range of 200 gigahertz to 1 terahertz. And if you have an interferometer like that, then you can possibly make images like the ones shown here. The left one is the model. In the middle, you see a simulated image with just 2 satellites, but assuming that the whole interferometer is phase stable for months. And then you can see that you can reconstruct a number of features that are in the original model image. And then if your satellite system is not phase stable for months, which is, well, I guess this is also an ambitious goal, then you can use 3 satellites and closure phases to make your images. And this was demonstrated by Frick, Zulofs and company. So I think these are very exciting science goals. Full implementation addressing all science cases would require an L-class mission. Interesting idea, but if we optimize the science mission, then we can probably bring it down to an M-class mission, which has probably better chances. But if we have to point out that the key engineering components required for this mission are part of mainstream developments already. So that was my thought, and thank you very much for your attention.
Thank you so much, Zsolt, for your very interesting talk. Unfortunately, we don't have any time for questions, but the questions will be posted on Discord, and you can answer any questions there. I see that there are some questions for you.
I will forward them to Leonid. Thank you.
If you can please just remove your screen sharing so that we can go to the poster talks. So we now have our poster talks, the 2-minute talks. And our first speaker is Michael Janssen. And I will ask that Michael please share his screen.
Yes, thank you.
Thank you, Michael.
Okay, hope you can share. Should move this away. See my screen. So here I'm in this Gather Town poster reception app. My poster is number 16 here, so we can look at it together right now. And it's about something that was discussed in some detail actually yesterday, which is using CASA to reduce your VLBI data. And this poster is really just meant to help VLBI users getting started with using CASA. At the end of the poster, there's some links to websites that contain much more extensive information and also some very detailed tutorials. But this will hopefully get some users started. I just mentioned a few things about this poster, namely my mostly personal view of why you would want to use CASA for VLBI data. It is definitely very future-proof software, and is also actually able to scale with available hardware, scale with computational power. So it's actually able to keep up with the increasing data rates that we have in our radio facilities, future radio facilities, and also some of them, like the EHT that are already here now. Also CASA has been used for quite a while now by the connected element interferometer community, so ARMA and PLA, for example. And I think this is now a nice case to bring that community closer together with our VLBI community. So then here is some information on how to install CASA. Here, if you want to get started with the manual interactive data reduction, this is for a CASA session, how you would typically run a few of the typical data calibration steps. Most importantly, how to actually get diagnostic plots of your calibration results and of the data, so that you actually understand what you're doing and also ensure that you're calibrating the data in the right way. On the right-hand side, I give an introduction to CASA-based VLBI data calibration pipeline. So that's interesting for people who don't want to go through the tedious manual steps and who care about scientific reproducibility. So here's some general information, how to install it, how to run it, and the diagnostic plots produced automatically by this pipeline, highlighting here a few special calibration steps that are possible with the pipeline, but not yet with the native CASA installation. So these are, for example, scalar bandpass, atmospheric correction for Earth atmospheric opacity from the troposphere, and tuning of an optimal fringe fit solution interval. That's all. Thank you.
Thank you so much, Michael. We move on to our next speaker for the poster session, Susanne Lunz. If you can please share your screen and the title. Yeah.
Thank you. So you see my screen, you can hear me?
Yes, we can.
Okay, great. So my name is Susanne and I work in the VLBI group at the THEZA in Potsdam. Our study is in the field of astrometry about the alignment of the optically bright part of the latest Gaia data release to ICRF3. And alignment here in this context means calculating a residual orientation offset around the 3 coordinate axes of the reference frames and its time derivative, the spin. And it's known that this alignment is depending on the magnitude of the objects as seen by Gaia, and that the optically bright fraction has to be independently verified from the faint fraction of the Gaia catalog. Now, usually the ICRF3 is used for this verification directly, but there are no optically bright counterparts in ICRF3. As a solution, it was introduced by Lindegren in 2019 to use models of stellar motion and single epoch positions of radio stars from VLBI for this investigation. And because the stars are usually faint at radio frequencies, they need to be observed in the phase referencing mode. But the analysis lacks suitable VLBI continuum data of radio stars, which is sparse in sky distribution and in the time domain. And we improved this analysis by adding a position for 32 stars using the VLBA from the USNO time allocation at one epoch in 2020, and more data from various VLBI networks from our collaborating co-authors. This also allowed us to calculate improved models of stellar motion for 13 stars, which already had enough VLBI data. We also homogenized the data by applying ICRF3 positions to all the phase calibrators and by considering a realistic error budget for absolute star positions that we use. And in our poster, you can see how the analysis of the alignments changes with these improvements. And finally, a significant spin was detected. However, the various solutions show that the reliability of the results should be improved by more VLBI observations of non-radio stars, but also more optically bright counterparts between VLBI and Gaia need to be found to improve the orientation. We will, however, have another 3-year project which will work on this task, and any input and comments are welcome. Thank you.
Thank you so much. We then go to our next poster talk, which is given by Janis Steinbergs. Janis, thank you, Susanne. If you can please share your screen.
Can you see my screen?
Yes, but not your presentation.
So sorry, let me try again. So I can open.
Now it's gone.
Let me try again. So.
Okay.
Now you should see my presentation, yes?
Yes, we can see it. Thank you.
And also, can you see in the full screen?
Yes.
Okay, so I will start. So in my poster, I will show latest developments on urban baseline. So consisting of 2 telescopes that you see here in these pictures. On the right, 3032, and in the left, 3016. So I will move to the next slide. So what you can see is location of telescopes. So what we have is 800 meter single baseline with typical observations we've done with C-band receiver, and we have observations done using 16 BBCs and using 8 times 8 megahertz per each channel and each polarization. So we use SFXC correlator for our correlations, and we have developed partial tone pipeline for data processing and calibration. So let me move to some results. So currently we are focusing on one scientific goal, that is observe acceleration events in high mass protostars with methanol masers, particularly to obtain more evidence of maser bursts. And currently what we have achieved is sensitivity of 6 millijanskis for 120-second integration time. And what you see here is 2 results. First is flux over time of high mass protostar, and same high mass protostar you see cross-collated spectrum, and we expect to detect flaring of individual maser spectral components. And thank you for your attention.
Thank you so much. And then lastly, I think Kasi would just like to share a few words about the ideas mailbox for EVN users poster. Kasi?
Yes, I just wanted to, oops, right. So if you will go to Gathertown, you will find right here the EVN ideas mailbox poster right between the entrance and going to the lounge for having a beer. The EVN ideas mailbox is basically that you provide us the information so that we may improve the EVN, have it more user-friendly for you. And that's it. Please leave your ideas in the EVN ideas mailbox accessible at the EVN website.
Thank you, Kasi. And that brings us to the end of today's session. Again, thank you so much to all of the speakers, the poster presenters for a really excellent session and very interesting talks. And I will now hand over to Denise if she has any announcements. And yes, remember 1900, the poster reception in Gabbertown. Over to you, Denise.
Yeah, there are no notices, no announcements, but we hope you get a good break and enjoy the poster session this evening.
Maybe can I add a last detail for people who have not been to the Gathertown space? Please try that before the reception starts, because we will not be able to troubleshoot during the reception. But if there's anything, I'll be available an hour before to help.
And a huge thanks to Ilse, who did some furious work unseen to most to make sure that we did get access to the space tonight.
Yep, that worked out.